Thanks everybody for coming to this event. Please bear with me, I have a cold. I'll try to speak slowly. If I start losing my voice, excuse me if I turn the mic off for a second and cough so I can regain sanity and pick up where I left off. So, people are probably wondering, what is this all about? We took a look at the Raspberry Pi 3 when it was released earlier this year. We've been working for over a year with Opti and wondered if it was possible to actually make the software run on a Raspberry Pi 3. So I'll cover a few topics. So basically, what's our motivation for doing this in the first place? What was involved in actually doing the port? So what was the undertaking like? What's the availability of the components, all of the pieces involved? And then we'll walk through some of the core aspects of what the implementation means, sort of what's there and what isn't there, and then an overview of what the TrustZone is really about, because although you may see that label, it doesn't necessarily mean that everything's in place. So we'll give an overview of typically what we expect to find on a complete implementation. So we look at the motivation, and next generation devices, they need to have security designed in. The systems need to have it designed in. I think we're past the point in systems on chip where it's now a requirement or no longer required to bolt on additional chips or other parts. At this point, we're looking from several manufacturers, say call it 4th, 5th, or 6th generation implementations, where any security feature that was previously in a TPM or a high security device is now starting to appear in sub-$10 system-on-chip parts, for example, used in payment terminals. So some very high-end capabilities for security features now appearing on what I'd say are commodity parts. The TrustZone and the trusted execution environment are very quickly becoming a standard for chip-level security. So when you think of the broad deployment in terms of mobile devices, set-top boxes, smart televisions, these are very, very commonly in use going back several years. And one of the biggest challenges we find, though, in trying to bring this, say, to larger embedded space outside of mobile is awareness. Within the maker community themselves and within a lot of the manufacturers, they have no idea what this technology is, either from the standpoint of the hardware or the software or firmware that it entails. So unfortunately, where this leaves you, the only people that understand the technology are hardware and software professionals that really know how to wade their way through a data sheet or understand the details of the stack. And because a lot of this has been sort of kept under non-disclosure and wraps, it's really not a well-understood space. And even to build this, you have to have a very deep understanding of the hardware and the software fundamentals of the systems as well. So the objective for this port is really to make this all accessible and make it economically accessible. So what's our motivation? The Raspberry Pi is really inexpensive. In no volume, it's a whopping $35. There's very good support for it. So the board support package from the Raspberry Pi 4 from the foundation, it's a quad-core A53 V8A part. So it's a recent ARM core, so a very good learning platform. The starting point for us was back in March when initial work had been done to port a 64-bit stack to the Raspberry Pi 3. So we watched closely to see what was being done. We poked around the startup code. At this point, they'd stepped sideways from the normal boot mode for the Pi 3. We poked around and it looked like there might be some TrustZone capabilities or features available on the device. Searched for JTAG capabilities for low-level debug and found in previous versions that there'd basically been multiplexer pin setups for the 40-pin header on the Raspberry Pi and started digging around to see if it would be possible to do this on the Pi 3 as well. Our intention was to make it available so that you could bare metal debug on the Pi in all domains. And it appeared if a port of Opti might be feasible. So the work was done largely late March, early April, looking through what was happening in several of the Raspberry Pi for us surrounding ARM64. If you go online, you'll find sort of the initial work initially in porting U-boot and the initial port of a 64-bit Linux kernel. Digging into U-boot, naturally they were U-boot was bringing the cores up in the wrong mode from the standpoint of launching into a secure world. So the first step was basically modify the U-boot stubs or the pre-boot stubs to bring U-boot up in the right mode so that we could then begin the port and do the correct handoff. And our initial objective was to get a 64-bit Ubuntu environment up, so we used the Linaro native Ubuntu environment, just dropped it in place. The details of all of this are actually in a separate PowerPoint or a separate presentation. If anybody's interested, we can make that available. Some of the challenges. So I did the port myself in a weekend. And typically this means for any SOC, going to a vendor, signing non-disclosure agreements, then signing away the firstborn to get the other documents that they don't give you out just because you have a non-disclosure agreement, to learn about the underlying details of the SOC. For the Raspberry Pi, effectively there is no data sheet. So what's inside of that is a bit of a mystery. It took guesswork to come up with a memory map that was actually workable, and about 6 iterations of guessing to find an address space that we could work with in memory. And the other source of information is to dive into the source code, or the expression we use is, use the source, Luke. So the approach, again, we have details in the other write-up, was to modify the boot stubs to leave the cores in secure mode, modifications to U-boot to hand off to ARM trusted firmware instead of to the Linux kernel. So looking at, people were asking us if we would port all of the ARM trusted firmware, and reading through the documentation, it became evident that ATF was really architected so that it would be possible to have an alternate boot chain lead to BL31, so next to the second last phase. And we worked out how to basically do a handoff from U-boot to BL31 to hand off to the OPTI service provider. So modifications to BL31, modification to the memory map, so because there's effectively no secure memory, we create a hole in the middle of physical memory and drop all of the secure stack in there. In U-boot, we do the pin multiplexing so that JTAG is enabled very early. So in the kit that we've assembled, as soon as the U-boot prompt appears, JTAG's already enabled on the board. We also took work that we did last year, which was basically OpenOCD support for ARCH64 for ARMv8, and worked out the configuration file for the Raspberry Pi so that you can actually use OpenOCD and an inexpensive JTAG interface to debug the board. And then we ported over OPTI. That was actually the easy part. The hardest part was the memory map and sorting out the serial port interface. Yes? Off the top of my head, I don't recall. I don't remember. I basically derived it from another fork. So I looked at a more recent version. I don't think the handoff has changed. Effectively the setup for it goes passed in through register 0, and it's a matter of populating the structures for the handoff to the secure and not secure domains. But there was only one place we had to make a change. Basically, one of the debug settings they had was conflicting with the core clustering with debug enabled, so we just turned that off. I'm not going to say it's perfect. Go ahead. Because I really didn't want to rewrite BL1 and all the way forward when all the drivers are already done. I don't think I could rewrite all of the first 3 stages of ATF in a weekend. There's a lot of mystery lurking in U-boot in the Raspberry Pi, and it was like, I'm not going there. This is a lot of work. The objective was to get to the OPTI and the ability to develop there rather than to rewrite the ATF or port it. If somebody's willing to do that, go for it. Happy to help any way we can. And at this point, I think you probably could, given that you have U-boot handing off to ATF, I think you could debug it really easily. Just set it up. So anyway, the Raspberry Pi 3, the thing we discovered is it implements all of the core exception states. So in the V8A nomenclature, we have all of EL0, 1, 2, and 3. EL0 and 1 on the secure side, 0, 1, 2, and 3 down in the middle, and 0, 1, and 2 in the non-secure world. Unfortunately, the signal that's propagated off the core, so the security signal is left dangling in the air. It goes nowhere. So the cores can trap through all of the exceptions. You have the ability to execute the code, but there's absolutely nothing secure about the bus fabric of the device, as far as we know. The cores are also not the first thing that boots. From our understanding, it's actually the GPU that boots first and hands off to the ARM cores. So people have already asked, can you implement secure boot? And we go, not as far as we know. No indication that it's possible. One thing we did find actually in the course of doing the port is none of the crypto accelerator instructions are implemented in V8, so those are optional. They all had to be disabled, and you learn very quickly in bringing up Xtest that it will hard fault on instructions that are undefined. So easy to track down and discover was those instructions are missing. There was nothing in the Linux device tree source, so we did a lot of digging trying to understand what the IP looked like on the device. There was nothing show any indication of any security IP, so no mention of an address space controller or protection controller. The interrupt controller is proprietary. Sort of another giveaway was that FIQ was being used by, I think, a USB or audio component to reduce latency, and as soon as we brought Linux up in the normal world with opti in the back end, FIQ fired and the T went into an infinite loop because FIC is not supposed to go to the normal world. So easy to fix that. We found no indication of securable memory, so it's basically one big flat space with a region carved out in the center. But the really good part, and the last piece, I guess, there's no signal propagation. So everything that you would want to do to try and carve out an isolated secure domain is just not present on the device. So our conclusion is, it's a TrustZone implementation, but it's not secure. But the really good part is, it's so unlocked and so wide open, then it's phenomenal for education and phenomenal for debug and development. You can single step with practically free hardware through the exception levels and actually see what the code's doing. So for us, this was really a great help, because often at the hardware level, signals can have interesting latencies, and even trying to step across boundaries with a debugger attached sometimes doesn't work. On this device, you can walk right through the code. So availability of the kit. I sort of cobbled this together and handed off what I'll call a bit of a wheelbarrow full of stuff to Joachim Beck. He took this, I think it was like 27 steps in a script to build the whole stack up and pulled together a repo build with a BusyBox stack. He went a lot further than that, and I'd say it's probably the slickest development environment I've seen. I didn't know that U-boot supported TFTP boot. So he has a configuration, and what's coming in the Linaro build is effectively U-boot to TFTP with a file system for the Raspberry Pi over NFS. And this basically means you can basically boot and develop entirely off the host development machine with minimal cycle time. So no fussing with wires or power buttons or anything like that, or having to pull SD cards or reflash anything. You can run it entirely off the host file system. So for cycle time and TA development or core development, this is really a brilliant move. It's extremely fast. That stack is all ARCH64, but that's fairly easy to change. In a little over a week, we're actually we're providing the hardware for a global platform T-hackathon in the Bay Area. And it was suggested to us that perhaps we could run a 32-bit stack on the board. So what we've done is basically taken the ARCH64 Linux. It's built with the config compat flag, which allows us to run either 32 or 64-bit runtime. We took the Raspbian stock out of the box Raspbian 32 build for ARM v7, added in the components from opti, so the driver in the kernel, the T-supplicant, and the set of TAs, and dropped this onto the Raspberry Pi. The kernel complains an awful lot about deprecated instructions from v7 because we didn't recompile, but it works fine. We built a VirtualBox Ubuntu image that includes the full all source code for the stack and all source code, including the OpenOCD port. And the whole kit itself consists of the Raspberry Pi 3, a bus blaster, debug cable, a micro SD card, and I think the total cost is probably in the $70 range for everything. So pretty hard to beat, including the debug interface. The focus itself, so the Linux stack itself, the Pi is really in widespread use. It's great for development, and from our perspective, it's not a mobile device. We have a license to deploy trusted applications on mobile devices, and we're totally familiar with that ecosystem. We look at something like the Raspberry Pi is meant for, call it other nodes, other smart devices, a great platform to learn and develop for those. So I'd say very different ecosystem, very different use case, very different set of applications than mobile. And for Opti, I'd say the focus is much bigger than mobile. We call it the other 90% of the market. So fundamentally, the applications that need to be built go well beyond, say, DRM and payments. So these are sort of the obvious use cases if you're deploying millions of applications out on mobile handsets. But when you think of edge nodes, gateways, smart devices, and a variety of other things, there's a good chance that a power meter is not going to be taking payments from your credit card or has a touch interface. Right? Just think of the other use cases for this and what can be done with with the technology. So I'm going to walk through some background. People ask us, what's the point of security? What's it all about? It's really about creating a boundary. Security happens at a discontinuity. Go ahead.
Sorry, it's a quick question. 2 slides ago, why choose a 32-bit?
Because for people that already use the Raspberry Pi, we give them something that they already know. So there's nothing stopping them. They can have 32 or 64. And actually, we've taken the Raspbian 32 system and dropped in 64-bit shared libraries and a 64-bit loader and run them both at the same time in the same place. The kernel doesn't care. Just make sure if you're building kernel modules, they're built 64 bits. So it's up to you. And I mean, we've done them both. So Linaro has a 64-bit stack. You can run the 64-bit stack. And for debugging the normal world, you can run the native GDB tools on the software on the board. So it's more the familiarity of people. When they turn the Pi on with an HDMI, with HDMI plugged in, they will get the standard Raspbian experience, if you want to call it that. So we call this the problems of a big flat space. Security has to be designed in, and the objective is to create isolation and a boundary. So security happens at a discontinuity in the system. And the trick is there has to be some mechanism that enforces that discontinuity. So the objective is to create a hard boundary. So something that's hardware enforced, not just an address, not something magic like an address. There's got to be a signal behind it. So there have to be at least 2 distinct domains that can be partitioned beyond that. So call it secure and not secure. And within those domains, you should have the ability to assign code, resources, functions, and without requiring some external security component. So if you look at the architecture of some of say, an advanced SoC today, you'll find that there's no shortage of on-chip IP that's evolved over the course of probably the past 20 years. And they're, I'd say, much more highly evolved than the average desktop PC. So it goes well beyond the capability of what's in that box for certain. One of the objectives from our perspective is to isolate management and control planes. So when you think of the critical functions of a system, isolate management and control in the critical functions and treat, by definition, the operating system such as Linux, it's not secure and it's not trustworthy. We don't care if the network stack gets popped. We don't care if the normal world gets compromised. The whole objective is that what's going on in the secure domain in terms of interaction with, say, actuators or sensors, and the control of those is isolated from anything that can happen in the normal world. The point is, don't have to trust the network and don't have to trust the application stack, but you do want the core components, the critical components, to be trustworthy. So it starts at the bottom and build up, and it's really hard to bolt this on. It has to be designed in. So we look at it. TrustZone's not a marketing term. It's a strategy. The beauty of it is the security, let's call it, it's the security state, not a mode. It's orthogonal to the processor mode. So the processor runs either secure or not secure. In each of those states, it has the various modes that support operating systems and exceptions. There are 2 states, secure and non-secure. The physical domains themselves, when you split between those 2 states, so you have memory, on and off chip memory, the ability to partition and manage that. You have bus masters and slaves, and there must be a mechanism to define whether a bus master or slave is secure or not secure and when. That has to be propagated throughout the bus so that a non-secure master cannot access a secure slave and vice versa. So you basically want to not have the conflict of a back channel through the fabric. This also has to basically permeate through all interrupts and caching mechanisms. So the caches have to be appropriately segregated as well. So typically at L2 or at the point of unification, the caches also appear independent. Even though you turn on an L2 cache globally, whether it's secure or not secure is still appropriately tagged so that you're not stepping into the wrong place from the non-secure domain. There's a lot more to this than crypto. So we look at it from the standpoint of effectively implementing driver stacks as well. So somebody says they want secure storage, put the quad SPI interface in the secure domain, put the chip on a separate bus, put the driver in the secure world, and your storage and your boot blocks are now outside the region of the normal world, just being able to do an easy hack in Linux to get at the boot region of the flash. There's a lot more that starts before this, and it's typically very much, and I'd say this is going to not change anytime soon. There's been a lot of fragmentation for good reason. A lot of the silicon providers have invested heavily in effectively what is their proprietary IP. So anything involved in terms of planting root keys, what's embedded in their ROMs, all of their, say, proprietary IP in terms of segregation mechanisms, or the ROMs and how those work, they're all very much device-specific and vendor-specific. So what means secure boot? What means secure update? There are points where you can branch forward, but these are all SOC-specific, and they have to be taken into consideration when doing the design at the SoC level, as well as the board implementation, or what the OEM wants to build. What's involved in the cryptography really depends on the chip itself. One of the things we like about what the TrustZone provides with the appropriate software is it fails elegantly. So unlike crypto accelerators, how many people have watched the recommended minimum length of an RSA key go from 512 to 1024 to 4096 bits? If you embed that in hardware and tomorrow 4096 bits are broken, you're kind of left in the situation of either your chip's broken if you can't update it, your TPM or your external element's broken, or if you've done it in software, have a good implementation, well, you can update it over the air. So the failures are a lot softer. You just have to take a lot more into consideration when implementing it in software. And there's a lot more to this than just the crypto, because you can actually implement critical functions. So let your imaginations go wild and think in terms of, we think specifically in terms of sensors and actuators. What are critical functions on the device that really need to be isolated properly? And this allows us to implement trusted controls. So I don't know that there's an awful lot that I need to say on this side. It's sort of a summary, but effectively it's about separation, secure boot, secure firmware updates, authenticated payloads. This is a bigger deal than it sounds. You know, security is something really hard to sell, and you won't find a lot of C-levels who will actually say, yeah, I'll pay you 20 bucks a device for security. They won't pay you for security. They will pay you for IP protection. And if you say to somebody, well, we can protect your IP by giving you an encrypted boot chain tied to a root of trust so that nobody can steal your design, then they care. So if you turn around and say it's about basically protecting the integrity of the device or brand or reputation or not stealing somebody's IP, then they get really interested really quickly. The same thing goes for the manufacturing and provisioning. So that's sort of how security is the objective on one side, and on the other hand, the benefit is, wow, they lose less money and they have a better design in the end as well, and your thermostat can't be used as a garage door opener. So I'm going to walk through some of the underpinnings. Are many people in the room familiar with TrustZone or the terminology or the mechanisms that underpin it? I can cover this fairly quickly or fairly slowly. We always get asked questions like, how does this stuff actually work? So, is it in use anywhere? So we step back and look at it. It's been around for, say, over a decade. It's on more than 1 billion devices. So think in terms of Samsung, BlackBerry, Nokia, Microsoft. So you turn the clock back a long time, and this has been living under the hood on systems that we're not even aware of. Nobody talks about it. It's there. It's in pretty much every Samsung handsets that ship for, I'd say, the past 3 or 4 years. It's used in payment and bank terminals. It's used in set-top boxes. It's used in smart televisions, and the list goes on. So some of the terminology. TrustZone is hardware. The trusted execution environment, or the TEE, is software. It's the, if you want to call it, the operating system that occupies the trust zone or the secure domain. There's the normal world, the rich OS, the rich execution environment. So think of Linux or an RTOS. There's the secure world, secure OS, the trusted execution environment, OPT as an example. There's a secure monitor, which is a very special place. Sort of lives in between worlds. There's a trusted application, which naturally runs in the trusted domain. There are trusted connector APIs, so there's some piece that has to call from the normal world to invoke a trusted application. And then depending on the ecosystem you're in, there may be a third-party trust model for deploying trusted applications. That comes out of the mobile space. It's not necessarily applicable, and I'd say in the world of embedded or smart nodes. But it's really very, very use case specific, and be careful when going there because it can inject cost into the ecosystem that people don't like. So I'll give a review. People ask us, I mean, we get asked a lot of questions on this. So the trick is the CPU propagates its security state onto the bus. So the CPU is a master. And it effectively, when it's secure, it will communicate with secure and non-secure slaves. Non-secure masters won't talk, get it right. Non-secure can't go to secure. Effectively, you're blocked. All of everything on the bus fabric must enforce this. So if there's a DMA master that does not, then there's a good chance you have a back channel or a leak. So if you can get control of the driver interface for a bus master that's not being set up properly or you cannot bind a security attribute, then you've got a piece of silicon that I'd say is kind of questionable. And this has happened many times. People ask us, what is this? What is the trust zone exactly? Is it like virtualization? And the answer is no. The software is running on bare metal. There's no magic extra set of page tables doing an additional layer of interpretation on an address space. It is like a virtual second CPU, just happens to be the same one. So what happens is that the critical registers that represent the CPU state are banked. So things like the control registers for page tables, the physical and virtual address spaces, so the MMU effectively looks banked. And then the caches as well are split, as well as the controls. So the CPU in the secure world can have everything enabled, be running with the caches on, be running with the MMU, and step into Linux that's not got anything turned on yet, other than the clocks are running. There are two interrupt lines to the core. So FIC, fast interrupt, and IRQ. So by convention, FIQ is typically bound to the secure domain. The magic. So the core, if you're coming out of secure boot, the core resets into secure state. At this point, typically, is where the binding is done for the peripheral states. So you've got to find the mechanism, whether it's proprietary IP or ARM IP, what binds or what allows you to associate a security attribute with everything that lives on the bus. The cores are obviously secure at this point, but you need to designate, if there are peripherals you want to be secure only, mark them at this point and keep them there. Depending on the IP, it may be possible to flip peripherals back and forth between the domains on the fly. And obviously, should be under the control of the secure domain. There's this magic register called the SCR, the Secure Configuration Register, and it really is that. It's not accessible from the not secure domain. So when Linux is running in the normal world, that register doesn't even exist. And any attempt to read it or write it doesn't cause anything weird to happen. It's just ignored silently by the CPU. So this is the little magic register. Its least significant bit defines the core state. Linux can't even ask if it's running. If it's running not secure, it won't get an answer back. Effectively, that least significant bit, so it's inverted logic, not secure is 0, means it's secure. Not secure is 1, means it's not secure. There are a couple of other interesting bits in there. FIQ, IRQ, and abort. These are basically used for routing interrupts. So in the secure world, if you set the F bit to 1 and you step to the non-secure world, Linux can do all it wants to try to mask FIQ, but it can't block it. So if a fast interrupt appears, the core will trap to the monitor mode. And from there, it's time to dispatch off to the handler for secure interrupts. So the beauty of this basically means you can have a DMA master with an interrupt on it bound to FIQ, You can have this running behind the scenes, bound to a driver in the secure world. Linux will happily go do its thing. The interrupt fires, and you're now magically in the driver in the secure domain without a hiccup. It's very, very elegant. And Linux has no ability to block, so you have no way for the normal world to stage a denial of service attack on a resource or a clock, or let's call it a critical peripheral against the system. One of the tricks that's actually done or needs to be employed is the rerouting of interrupts on the fly. So as you pass between domains, if you get to the secure world and you block handling interrupts to Linux, you're going to deadlock very quickly. So as soon as the monitor enters, it actually switches the order around so that the interrupts are all delivered to the secure world. And effectively, the IRQ interrupt is delivered to the secure world, but it's routed back to the non-secure world through the monitor, through the driver, so that the normal world interrupts can execute. If you don't do that, a lot of things will break very quickly. So typically, and depending on what the interrupt architecture looks like for a device, if you bring opt up and you find as soon as you try to do anything, like say, for example, access a file, and the device locks up, it's probably because the interrupt architecture, the interrupts aren't set up properly. Yeah, and the last point, that the register is just not accessible, which is a bit of a revelation. This monitor mode, or in V8 terms, EL3, it's not obvious for a lot of people how this thing works. The monitor is entered from EL1 or EL2, so either secure or not secure through an SMC, basically a trap call. When the monitor is entered, the not secure bit reflects the state that it was entered from. But the monitor mode itself is implicitly secure. So whatever mode the core was in when you left to the normal world is the state that you're in when you're in the monitor. So and the page tables and the address space that are visible at EL3 are the ones that were set up on the secure side. So the address space and the code space you're running in are always secure. What changes with the value of that bit is which view you have of the banked registers. So from within the monitor itself, you can actually set the not secure bit, and you can go look at the page tables for the non-secure world. So we've had to do this at times in debugging. We have had to go in when we found really strange things happening and walk TTB0, TTB1 from the normal world in the secure world and map the pages in to find out what's going on. But typically, you don't have visibility because that's not the address space you're running in. And for a lot of people, this isn't obvious. For entering or re-entering something like Linux, you have to reset the SCTLR, so the control register that defines things like caching and MMU enable, because those are banked as well. But you can see what's going on in the normal world from the secure side. So bottom line for this, that code's really sensitive. Keep it as small as possible, and it should just be a pass-through. So effectively, context switch only, get in, get out, and don't do as little as possible in there. Don't stick around, it's way too sensitive. I'm going to walk through an example. So this is basically on, I guess we have some time. A little bit of the background of what the architecture is between a trusted application and the connector component that would call it, and the APIs that are implemented. So there's a standards organization called Global Platform. They implement a number of APIs for standardizing effectively the calling protocol between a normal world application and a trusted application. So they have two sets of APIs. Call one the T-internal API, and the other one's the T-client API. So the client runs in the normal world. The core API runs in the secure side. Effectively, there's a runtime library in the secure domain, and the internal API exposes this to you. So we have a set of predefined entry points, and they effectively provide the APIs to give you access to things like trusted storage, so for data or keys, cryptographic operations, time API, arithmetical. There's also, I think, advanced API has been announced for trusted user interface. So the idea is that you'll have a complete, say, call it the GPU and a digitizer, where the entire driver stack and the ability to interact that are within the secure domain. The big deal about this is that you can now do pin capture without phishing. I don't care if you steal my pin, the entire capture operation, the binding to the transaction and the request is happening outside of the normal world. So compromise Linux all you want, I just don't care. The keys are rooted somewhere else. And the entire operation is happening outside of the domain of a system where they're at risk. Anyway, the point of that, basically, their objective is to provide a set of standard APIs, and it's more also as part of their intent is to define the semantics of the relationship between the two sides. What you do with the APIs, entirely up to you. You want to write bad code? Write bad code. But the whole point is that they're attempting to define the semantics of how the T should operate and how the API should operate. Multicore, yes. Yes. He basically asked if OpT supports multicore, and the answer is yes. Yeah, I mean, it has secondary entry points for as many devices as many cores as you want to bring through. The client API itself is very straightforward. Effectively allows you to define 4 parameters. It's fairly basic, much like an IPC. You have in, out, and in-out, so quite basic. It's very straightforward. In the case of OpT, the implementation let's say by requirement and definition, anything coming from the normal world is in shared non-secure memory, because the normal world doesn't have access to secure memory. And the passing is done at the physical level. So physical address space is common to both secure and non-secure domains. Addresses of pages are passed physically, and they're remapped onto the secure side as required. So effectively, the secure domain can see into the parameters that were passed. So a zero-copy interface. How it's implemented on other devices, you could do this asymmetric multiprocessing or multiple cores. Effectively, the whole point is transferring information through a non-secure channel. The APIs themselves, they can be blocking. It is possible to cancel operations. So from another thread, you can request that a command or a secure operation be aborted. And they're actually pretty straightforward to use. I just say it's very basic. So when you're staring at something, it's effectively like you're stuffing values in 4 registers, and you have to feed pretty much scalar structures across. If you pass a virtual address and a structure from the normal world to the secure world, well, it maybe will map. I'd say a good chance it will just abort, because the mapping won't exist. So all that work is left up to you in terms of in terms of making your structures scalar for passing them across. The result code's really simple. This is a tradition. 0 is good. Otherwise, you'll get an origin back on where the likely, call it the domain of execution, what went wrong. So whether it's within the API, communications, the T itself, or the trusted application, it gives you a hint as to what went wrong. The beauty of working with OpT is you can debug it to whatever extent you want, and you also have nice print capabilities. I don't think there's an implementation that doesn't define a serial port. So you can actually get a lot more information out of the system than you'd normally have in a lot of environments. There's a concept of a context in a session, so you can have multiple clients invoking a TA. You can have multiple connections in. TAs can invoke other TAs. So you can do quite interesting and hairy things with this. And I'd say whenever we run into a lack of understanding of the APIs, or in other words, when we don't know what we're doing, we typically go to Xtest. So go to the test suite. It's really elegantly done. Effectively proxies through the trusted application APIs to the normal world, and will give you really good overview about how the API should be used. So from our perspective, when we run into situations, either debugging the T itself or go to Xtest to understand what the original intent was. It's done quite nicely. The concept of the API is, so you define effectively an enum type. So it's like writing an IO control. You can define your commands as 0, 1, 2, 3, 4, 5, or pick whatever set you want. And you have a switch routine on the other side that dispatches out to whatever sub-functions you want to implement within the TA. So very straightforward, very, very basic. And the shared memory, up to you to define how you use them. It can be temporary, or they can be I'm trying to think of the term and I'm losing it, persistent objects. The context is represented in its own type, and just use null as the T name, because typically there's not more than one T running on the device. The sessions are represented by a session object. Naming by convention is through UUID, and the intent of this is, these are really big numbers. I think everybody in here probably knows what a UUID is, so know what the TA is, and that's what you're invoking. There's one unfortunate part of this is, from the secure world, you really don't know who's calling. So a TA receives a request to open and load, it really can't know who's calling from the normal world. And by definition, it can't trust it. So keep this in mind when you're building your stack and your applications, that whatever data or the application that's calling in or calling out, think in terms of what it means to have a rogue application in the normal world invoking the TA. So you have to look at what's passed across that boundary as well. Because it's well, by definition, the normal world is not secure. So you can't trust what it's doing. You have to think defensively in writing your TAs as well. Yeah, I'll gloss over this. Commands themselves, 32-bit integer, very straightforward. It's up to you to define what they do entirely. So it's very, very basic. 4 parameters, in, out. The parameters are optional as well, so you can put them in whatever order you like. Debug. So I think Global Platform may actually define an API for this. The beauty of running with Opti, if you have a device that's as unlocked as the Raspberry Pi, you can attach up the JTAG dongle and debug to your heart's content at source level. So if JTAG, this is another thing on SOCs, typically JTAG enablement is split by domain. So you may find if you buy a board that it may have the TrustZone populated or unpopulated, but whether or not you can actually JTAG debug in the secure domain depends on the SOC and the implementation. So you may find JTAG just will not work and it's not your fault. It's probably because it's been hard disabled. If you're shipping a device into the field, you almost certainly want to disable secure JTAG. You don't want anybody poking around in there. In fact, you probably want to disable all external debug. Worst case, if JTAG's disabled, you basically can run with dmessage or more or less printf. But it's better than running blind. The T client itself, so the client code, this is native Linux code. So it can be effectively represented as a .o. Whatever you build is a .o, a .a, a .so, link on the fly, do whatever you like. They're debuggable with GDB. So if you're running natively on the device, you can debug the code right on the device itself for the normal world. Or if you don't like using a debugger, you can use printf. Yeah. Yes, you can. Yes, you can. Yeah. So that depends on how you've built the boot chain. So typically, in the environments where we actually support Opti for production, the trusted applications are encrypted and signed, and they're locked to the root of trust on the device. So whether they live in the normal world file system or they live in external storage, effectively the normal world is blind to them no matter what, and if they're corrupted, they will not load. So the whole point of those is they're encrypted and locked to the root of trust on the secure side. Normal world has no visibility.
So supporting for that encryption and loading is
There's a basic capability in Opti for that. But the other experience that we have with other silicon and other implementations, we've written a pile of code that's very much silicon dependent to deal with the managing and the loading of TAs. That's a detail. And I mean, if you do a static TA, then that's baked in as part of the firmware. But it's something, as a basic, I think there are a set of headers, so there's a tool that will actually do a basic signing. The hook points for implementing this in Opti are all there. But at this point, I would say there is effectively no standard for defining how this should be done. But they should be locked to the device. And as well, we ask OEMs, if they want to do dynamic provisioning, I'd say 90% of the time for smart devices, the answer is no. They'll bake everything in.
Sorry, just probe a little bit further. You have to do a fair amount of work. Was the work mostly on the dynamic linking, supporting the task part, or on the authentication and decryption?
The task loading and the relocation of the ELF binaries is all in there. Okay. All of the code that does the dynamic relocation and the memory mapping it's been there for as long as I can remember. So it's effectively a relocatable ELF binary. But that's encrypted and signed, and that's the place where there's effectively stub code right now.
Got it. Thanks.
But all the mechanisms are there, and all of the hook points for you. I mean, ideally, what you want to do as well, and I'll say the reason it's implementation defined If you have a hardware root of trust and say on-chip crypto accelerators, you want to make use of those. So it's very much SOC dependent in terms of the accelerators or the capabilities that are available. And if you want to use ECC instead of RSA for performance reasons or key lengths, then it's really up to the tool chain you build around that. So the whole objective, and this comes down to IP as well. Part of it will be on the TA. If they're doing something that is critical, they don't want that code to be tampered with. So even the TAs, you can lock them that way. If they want to implement proprietary algorithms, say for even doing basic math, people have asked this question. So when I go to the TrustZone, it's slower, right? It's like, no, it's not like we deliberately slow down the CPU clock when we change contexts. If it takes 100 clock cycles in the normal world, it takes 100 clock cycles in the secure world. And the transitions are very fast. I'd say no worse than actually jumping between, say, user and supervisor on the core. It's a context switch. I wanted to make that clear. It's not slow. The point of the UUIDs, the intent is to make them unique. I guess in a larger scope, they would be managed so that there's no chance of collision. The point on the TAs is, it's a valid point. So how these are managed in terms of TAs, it depends on the ecosystem. If you're the OEM and you're assuming the risk for, say, something like a gas range, the risk is that it's going to explode if you put it online. You're holding all of the risk of putting the device online in the first place. I don't think who holds the key is going to matter. If the device blows up because somebody popped it, then that's the bigger problem. But it depends if you're going to allow someone else or you want a third-party trust model. That's when you're going to have or be able to delegate signing capability for the trusted applications over to someone else. And it's very much a business and ecosystem consideration. This is really basic, and I don't know that I think we're running almost late, so I want to finish up fairly quickly. Effectively, the type for an operation. I think the presentation is already available online. I can just fly through these fairly quickly. You don't want to hold people up from the end of the day. The shared memory effectively changes ownership for the duration of operation in the secure domain. So when it's normal world, it's owned by the normal world. Obviously, when it's in the secure domain, it's owned by the secure domain, who has possession of it. The core is not in both states at the same time, we hope. The buffers they're temporary references. So effectively, these are mapped in potentially to different virtual locations. The beauty of this is when you send down a virtual address from the normal world, you'll get it a different virtual address in the secure world, and it will be the right place. It just happens by magic beautifully. Yeah.
You mentioned that, of course, not being safe at the same time, but you also mentioned that you have multi-core systems.
Yep.
So you've got one core secure state, one core in normal state. So how do you ensure that buffer is?
So if you have the TrustZone protection controller running on the memory, if you view it as being one massive peripheral, the TrustZone protection controller will enforce the state of that's bound to the memory region against the accessing bus master.
Okay, so you do that rather than a copy of.
Yeah. Leave it if the hardware is done properly. So if you think of a core being not secure, it's not going to be able to get to memory that's been designated secure by the protection controller in a region.
That's true if you only access it with non-cache attributes. If you're trying to use cache memory.
If it's cacheable, if you're at L2, the security state is bound to each domain as well.
Sure, but if as you said, it's non-secure memory being accessed by the secure side,
Oh, you can do that.
then that doesn't hold true.
No, but you can go from the secure side looking at non-secure. It's the other way around. You don't want to go.
The point was if the marked memory is secure,
Yep.
actually a DRAM is the trust zone controls it between caches. And from the secure world, you're accessing memory not as non-secure,
Yep.
but as cacheable.
Yep.
You're looking in the caches as non-secure.
Right. So you have to mark the page table attribute correctly to step in the right side and the appropriate side of the cache.
But at that time, the non-secure side can look in the caches of the memory non-secure side. It will never go down to the trust zone controller to be protected.
Right. It will see the non-secure side, and what it's seeing in the cache may not even be coherent. Actually, it should be coherent, because if you have the paging set up correctly, the secure side will be using page tables that are marked non-secure for the cached region.
So my
Yeah.
point is if you did all of that, yes, the secure side, the non-secure side will be coherent.
Yeah.
Another non-secure CPU can alter that buffer while the secure side is looking.
Could do it conceivably. That's not, I would say you have non-secure accessing non-secure. Yeah, no, I agree. Yeah, yeah, no, I mean, and I'd call that actually probably a race condition or a bug, or somebody's deliberately trying to mess with the secure domain. Right?
In terms of security, yeah.
Right, at least it's not creating a breach situation. Okay, yeah, but I mean, one core is not in both states. Two cores are different.
You can't trust that buffer until you copy all that data into this.
Right, right, and I don't think there's necessarily a mechanism to allow locking of it. No, there isn't one. You basically can't get an exclusive lock on it. At least not one you could rely on. The only thing you could do is change the attribute to secure on the fly if it's possible. And that could, exactly, this will cause other problems. Yeah, you can't. By definition, you can't. Yeah. So anyway, back to the concept. So multi-threading can get a little bit confusing. So it's possible to have multiple handles and multiple entries into a T at the same time, into a TA. So I'd say be careful. So you may have unexpected consequences. So think carefully in terms of writing these. The reentrancy can cause problems. We've experienced this. So it takes a little bit of creativity to manage threads and avoid the problem in the first place. It's possible to cancel a TA, so typically what you would do is start a second thread or just do not a full fork, a clone, and effectively from the clone you can cause a cancellation to take place. I think I'd probably skip this. This is actually all online within the opt repositories as the basic example. So effectively, a TA that prints hello world. Very straightforward. And I think that's the end of it. And my apologies for running over. And thank you for your patience. So I guess any other questions?
Yes. So I have one very short question. Just to confirm, earlier you were saying that the OPT is already a multi-core ready. I assume that means it's also having, you know, like spin lock, mutually exclusive synchronization between the cores among themselves, right?
There is a mutex within the T itself.
Yeah, the multi-processor. Okay, so that's the short question. A little bit longer one is the, you look at the OPT, but there's actually a bunch of other secure OSs like Trustees, like L4 based. There's at least one more popular one that is blank on my note. Have you looked at the others and how do they compare? What is your opinions?
We have a license for one of the others. They're, I'd say, the dominant player in the mobile sector. They have a good implementation. The thing that I think will happen is because Opti is open source, it will probably dominate. I'm familiar with the code going back several years. The original architecture was very nicely done, well architected. The implementation is clean. The code's been refactored. We've been watching it very closely.
What about Trustee from Google?
Trustee, I think that's a derivative of TLK that came out of NVIDIA. I've looked inside of it, and I would say if you can't walk the monitor code in less than an hour, you're probably looking for trouble. Just my personal opinion, but some of the things that were done in there are a little bit hairier than I'd like to see. It's the code's more complicated than necessary, and I wouldn't want to guarantee that there isn't a means of getting it wrong. You know, so that's just my personal experience looking at it. I couldn't take it and build it and actually run it to exercise because there were missing pieces. I mean, my preference as a starting point is either I buy the whole product and work with it, or I have a license and somebody standing behind it. If it's open source, I want to build the whole thing and tear it apart and walk it closely. And have many sets of eyes doing that.
Are they mostly pretty much the same in terms of their goals, objectives, or they're actually driven by slightly different criteria, try to be different beasts?
The inside of TLK is actually different. They implemented an internal scheduler, so it supports capabilities, I'd say, that go beyond what's in Opti or beyond what global platform would define. I mean, typically, trusted execution environment historically has been more of a, call it a tokenized subservient interface. What they built with TLK went a little bit beyond there by putting a native scheduler in. So if you have the ability to designate a separate clock, you can run native threads. You then can run in, I mean, that creates a little hairier situation if you need to have either competing or dueling schedulers running between the two domains. And that's one place where I can't comment because I really couldn't load it, build the whole thing, and play with it. I looked inside the code, I would say it probably works. I just can't say anything about it. I'm not familiar with the silicon that it runs on either.
Thanks.
I mean, I know the environment, though it's sort of the dominant one on mobile. that comes out of the UK, and I mean, I think they've done a pretty good job of it. But I would say, watching the progress of Opti, I think it has a very solid future. I think it can actually take the lead and run. And I'm not just being biased on that. I've been working on the inside of this personally, I've been working on it for more than a year as well, and watching what's going on and watch very closely. So I think it's going in the right direction. I think a lot of promise. And I mean, if any of the other core people that work on it as well, would like to say anything, by all means, please, don't hesitate. I sort of come in from the outside, but I have a biased view because we've done a lot of work on it. Any other questions or?
I was just interested, thank you. I was just interested, I came a bit late, so you may have covered it already,
That's okay.
but the debug with OpenOCD and the Opti and the Secure World and Linux, have you got all that working? Is that working well?
Yes, so actually that was, though, at the very beginning we walked through the motivation of the port, why we did it. I mean, the Pi is, combined with all the pieces together, came to under $70, including a bus blaster for JTAG. What we assembled in the kit and what will be going in, so Joachim has the basic, call it wheelbarrow full of information. We've pulled together the information for wiring the cable, but OpenOCD running in the secure side and ARM64 is all running on the board. So even the profile for the Raspberry Pi is in place. The OpenOCD code for ARMv8, ARM64, we've used that on about 5 different vendors, SoCs, and it pretty much works for, well, I'd say it's a lot less expensive than some of the alternatives. It's available, and the Pi, as soon as you turn it on, it's enabled in U-boot. So you can, and maybe for doing like basic U-boot feature development, you could use a Pi for that. But it's there, and I mean, step one for me is get JTAG working, and then on that I'd never worked with BL31 from the ARM Trusted Firmware, and that was sort of the means to walk the handoffs.
I'm just interested if you have, like, loading the symbols for Opti into GDB. Can you debug, like, the kernel and the secure bit?
Everything. In OpenOCD, we force hardware breakpoints.
Yep.
So the challenge between ARM64 and ARM32, if we enable soft breakpoints, the halt instruction is encoded differently. If you drop the wrong instruction into the wrong address space, the core will abort. So we impose hardware breakpoints. Next piece was the address maps don't collide unless you're trying to debug multiple TAs. So in the startup file, we load the symbol tables for U-boot, BL31, Opti, Linux, and in the case of the tutorial, or the case of the hackathon, we load the symbols for a trusted application as well. Those are all ARM64 binaries. None of the addresses collide. Okay, so when you're running Linux, you can Control-C and see that you're sitting, waiting in the scheduler, spinning around. And the breakpoints, because they're hard breakpoints, doesn't matter when you set them because it's up to the DAP to enforce. So you're not trying to change an instruction in the currently mapped address space.
Yep, that's really cool.
Yeah, it's quite useful.
So I have another maybe weird sounding questions. So instead of having TrustZone or the Secure World on ARMv8, what do you think about I just connect to an external TPM?
So TPM will, I'd say, limit you to cryptographic functions, and if the TPM is external, the thing that scares me are the bus probing attacks. So at this point, I look at it from the standpoint, if you attach a TPM, maybe there's some benefit for it, but from the standpoint of actually being able to build an application in a secure domain, how do you isolate memory and the peripherals at the same time? If you're going to add a TPM, I'm going to say bind it to the secure world if you need it for that. Otherwise, look for a device that has a properly implemented boot chain, OTP fuse set, and ROM, and you can probably, at this point, when I look at the defensive features that are available on a lot of TPMs, they represent potentially a lot of additional cost when you may be able to spend $2 more for your SoC and get similar capabilities. I mean, there are currently parts available that have die shields. They have on-chip tampers. They have voltage, basically voltage, temperature, and clock sensors. So you look at the chip sideways, and they'll dump their keys. So I mean, and this is state of the art. And moving forward, the higher level, the integration is coming on a freight train. So the companies that are leading in the development of these SoCs are already familiar with the capabilities. A lot of them sells TPMs. Some of them will, they almost compete with themselves in ways. But when I look at, the majority of companies, their objective is BOM cost reduction. So if they're looking at, I need to have another part for this, the answer is not really, not necessarily. It really depends on what you're trying to achieve. At the end of the day, it depends on what you're trying to achieve. But the thing that concerns me is the channel between the external element and the CPU itself. Unless they're mounted in the same package and you've raised the bar in terms of external physical attacks. You won't get the key off a TPM necessarily, but the data going in between them, you may.
Yeah, so I understand the security point and also the cost point you just made about TPM case. What do you think about functionality-wise if I choose that route compared with the TrustZone? Is there any deficiency, advantage, pro and cons?
I don't think so at this point. When you look at if you added a TPM to a device that already had a hardware root of trust capability, you've got a second device where you have to effectively manage and provision, so you've upped your provision and management costs. If I look in terms of what you can actually implement in terms of attestation functions, I don't think there's anything you can't done with an appropriately designed hardware root of trust on device. So if you're looking at things like remote attestation, you design the boot chain and the functions properly, so somebody wants to know that what's being booted is done properly. It's up to how you manage the keys and how you manage the boot early on when the device is coming up. I mean, we've been asked this. You can already get implementations of TPM APIs that are built on basically on a Cortex-A class device, and there's no TPM there.
Thanks.
Thanks. Looks like no other questions. Guess I'll thank everybody for your patience especially. Thank you.